This is lecture 14, and lecture 14 is going to continue on our discussion from last time, and we're going to talk about what's called the lasso. So last time, just as a quick recap, we had finished talking about variable selection, and we had talked about something called ridge regression. And ridge regression, right? So if you recall, for OLS, or ordinary least squares, our estimator of our function we got by finding beta hat, and I'll call this beta hat OLS, and we got this by minimizing our loss function L of beta across possible values of beta. Here, L of beta is our simple square difference, sum of squares, sum of square differences, you want to call it, which we can very simply write as L of beta is y minus x beta norm squared. And we had come up with this thing called ridge regression, where if we had variables that were highly correlated, x's, columns over x that are highly correlated, or in kind of the extreme case where we have more variables, a higher p than we have samples, that is rows of x, n, our beta hat actually wouldn't be unique. We'd have a perfectly kind of flat loss function along some dimension, and we wouldn't get a unique estimate for beta hat. And so the ridge regression solution was to estimate beta hat, we'll call it beta hat ridge, as similarly minimizing L of beta, but we added on some penalty, some norm of beta squared. And this penalty term, so this was our first way of interpreting ridge regression, would keep beta from getting too large. And the reason we wanted to do that is because if we have highly correlated columns of x, it tends to be that our betas tend to inflate a lot, and they tend to run off the positive and negative infinity. And to stop that, we'd say, well, let's just put a penalty on ridge regression to stop that. And so we'll avoid those solutions where beta is really large, and we'll prefer solutions where beta is smaller. And that helps solve the kind of non-unique problem, or close to non-unique problem, that we could run into. The second way that we had formulated ridge, an equivalent way, basically using some third semester calculus, was that ridge regression, you could look at it as minimizing our familiar squared error loss function, subject to a constraint that the norm of beta squared was less than or equal to some threshold value. We call it t. So again, this is equivalently constraining our possible values of beta, and keeping those betas from running off into some kind of wild area. Now here, lambda is just some number bigger than or equal to 0, and there would be, which is typically how you actually would compute this thing, is you choose your lambda. For a given lambda, there is a corresponding t such that this formulation would be true. And the third way of kind of thinking about ridge regression is that we could actually explicitly derive a formula for our beta hat ridge. It was x transpose x plus lambda I. So there's our tuning parameter, our lambda, not squared, inverse times x transpose y. So this is in contrast with our OLS estimate, which is x transpose x inverse x transpose y. So all we've really done is we've added on this lambda I, and this helps solve the problem if X is ill-conditioned, or X transpose X is ill-conditioned, not invertible. We add on some multiple of the identity matrix, we make this thing invertible. And so we solve the non-uniqueness problem that we could potentially run into. So ridge regression is known as a shrinkage estimator. And it's known as a shrinkage estimator for obvious reasons. It's trying to shrink beta. That's its primary mode of operation, is trying to shrink beta. And therefore, it's known as a shrinkage operator. So the question, I guess, that is begged here is, why is ridge regression called what it is? And we can give a little example of why it's called ridge regression. Which is that so imagine that X transpose X is ill-conditioned, so our condition number is infinite. Then if we look at, our space of betas, so maybe this is kind of a toy example if we have 3 betas, and we look at our L, our function L, it's going to be some surface. I guess this should be L of beta, right? So let's say we have beta 1, beta 2, and maybe they're perfectly correlated, and our z-axis is L of beta. This is some surface in kind of 3 dimensions, and it's kind of hard to draw here what this surface looks like, but it's some 3-dimensional surface, and I guess we want to minimize this, so let's write it the other way. It's some bowl-shaped surface, right? Let's draw it like this. So our beta hat should be down here, ideally, and then it's some bowl-shaped surface that we're kind of not particularly well drawn, but it looks something like that, right? Okay. And we're trying to find the minimum of this surface. If it turns out that X transpose X is non-invertible, there's some dimension here. There's some direction where the loss function is constant on, and it's kind of a ridge. And, if we, go to either side of this, we might have a loss function that's curved. But if you move along this thing, it's really it's a constant value. So maybe I should draw that more as it's a constant value as I move along this ridge. And this is really hard to draw a 3-dimensional picture here. But that is basically the scenario that you end up with if X transpose X isn't invertible. There's some direction. It might not be a cardinal direction, beta 1 or beta 2, but there's some direction you can move along where you wouldn't change your loss, hence we don't have a unique solution. So you basically get what looks like a ridge. So here's maybe a better illustration. This thing looks like a ridge. And to solve this, we kind of bend the ridge here. So we solve our issue by bending it and creating a new unique solution so that we get rid of the ridge here. So you might be more aptly call it the get rid of the ridge regression. Okay, so that's nice. It helps solve one of the reasons that we might want to do variable selection, right? So why do variable selection, right? We had talked about 2 lectures ago that we could solve this with variable selection, and one of them was that we would have, say, highly correlated variables, and the other was kind of interpretability, is that we might want to just select out what the most important covariates are to include in our model. Now, ridge regression helps kind of in a kind of continuous way solve this highly correlated problem, right? So you could just throw out variables, throw out things that are potentially highly correlated, and that would solve this problem. And Ridge does that in a more continuous way. And so let's look at the second problem, which is, well, the other reason we want to do variable selection is because it just gets rid of variables out of our model. The problem with a Ridge is it doesn't get rid of variables in your model. It might constrain the beta hats so they're somehow more well-behaved, but it doesn't really get rid of variables. It doesn't help with interpretability of the model or simplification, which is a goal we might have when we do variable selection. So let's look at the second one. And we're going to have an aside here, although we'll get back to the main point pretty quickly. And the side is going to be about norms. So for vectors, we define a norm, right? And the classic example is the Euclidean norm, right? So if x is some element of a p-dimensional space, then norm of x, we say, is the square root of the sum of the elements. That goes 1 to p squared, right? And if we consider, say, the set of, let's say, the set of y such that the norm of y is less than or equal to, I don't know, 1, some value, this defines a certain circle, right? This defines our unit circle here. That set of all points, I guess, would define this disk more properly, right? That's what it would define. This formula is actually pretty generalizable. And one easy way we can generalize is we have a 2 here, and a square root, and we could change that to something else. So let's say q is some positive number, or let's say greater than or equal to 0. We could define the, let's say, q norm as norm of, let's say x, and we'll put a little subscript q here to note it's the q norm. And we're going to define it similarly to the Euclidean norm. So we're going to look at the sum of my elements, of my x sub i's, but we're going to, instead of raising it to the second power, we'll raise it to the qth power. And instead of taking the 2th root, the square root, we'll take the 1/q root. So this is kind of straight up generalization of that above formula, where I've just replaced 2 with some other number, some other positive or non-negative number. So when here we have q is equal to 2, then we could say x2, which you've seen me accidentally write sometimes, is the Euclidean norm. So this q norm includes our, favorite Euclidean norm. But we could look at other values of q. Maybe q is 1. In this case, we'd write it x with my bars, and we'll put a little subscript 1. This thing is called the, let's say, Manhattan norm. Or, more simply, the 1 norm. And the 1 norm is, we can actually write it out, right, is the sum. You know what I'm forgetting? I'm forgetting something in my formula. We need some absolute value bars. So in the case where q is 2, we don't need absolute value bars because absolute value of xi squared is the same thing as absolute value of, or non-absolute value of xi squared. But we're going to need some absolute value bars just to make sure this thing's positive. So it's actually the sum of the absolute values to the qth power and then that whole expression to 1 over q. So in the case of the 1 norm, it's actually just going to be the sum of the absolute values, right? To the 1 power, to the 1 power, right? So the kind of q drops out there. And so this is just the sum of the absolute value. If we look at, for example, we could look at the set of, let's say, y's where the 1 norm is less than or equal to, let's say, 1, some value, doesn't really matter. This is going to describe not a circle, but a rhombus or a diamond, or kind of a square on its side. So while in the 2 case, we got a circle, if we look at the set of all things where the sum of the absolute value, this is going to be that shaded region. This is so-called the Manhattan norm because if we look at a grid of streets, say Manhattan, and we want to look at the distance from some point A to some point B, if I'm in Manhattan and I want to go from point A to point B, I can't go through the buildings, right? I can't go through the blocks. What I have to do is I have to take my taxi on the streets. And so you end up going like that route rather than directly through the buildings here. And so if I look at the distance, the so-called Manhattan distance from getting to A to B, where I can't go directly through the buildings, I have to drive around the blocks. This is just the 1 norm of, let's say, A minus B. So you could say that distance 1, the Euclidean distance, which would be the 2 norm or of A minus B, would be going directly through the buildings, right? And so the Manhattan norm and the Manhattan distance tells you how many blocks you would need to travel. So it's a different distance metric. And in this case, you have a set of all things that are constrained or bounded in the Manhattan norm, gives us some kind of rhombus. But you can do this for other values. So, if I look at, let's just draw our axes. If I look at the case where q is equal to 2, I get that shape. If I look at the case where q is equal to 1, I'm going to get this shape. I could look at other cases, though. What if I look at the case where q is equal to 3? Well, I'm going to get some kind of ellipse that's going to be bigger than, it's not quite a circle, it's some kind of ellipse. It's supposed to be a real ellipse, but it's going to look kind of like that. So these points here, this is the point 0, 1. This is the point 1, 0. This is the point 0, -1, and this is the point -1, 0, right? And if so I'm going to get kind of this nesting, whereas if I go to larger q's, I get these more and more elongated ellipses. In the limit here, you could look at the square, which is going to kind of encompass all of these. So something like that. That's basically when q is infinite. So the so-called infinite norm, or the max norm, right, is basically the limit as q goes to infinity of this. And it turns out it's going to be the max of the absolute values of these things. So that's interesting. And that is defined by a square. On the other hand, you could go inward. So you could, and I'm going to run out of colors here. Let's get some more colors. Let's see, maybe orange. I could try a value of q less than 1, and I'm going to start getting this weird kind of, not drawing this well, kind of shape like that. So this is maybe q is 1/2. And it's going to start kind of, it's supposed to be symmetric around this, but it's not quite symmetric. It's just kind of squishing in towards the center. These are kind of semi-norms. They don't really satisfy all the properties that a normal norm does. For our case, it's good enough. If I look at, let's get one more color. What do we want? Pink. You could imagine in the limit, I'm basically just going to get, I'm going to end up on my axes. So you could think of x0, which is kind of the limit as alternatively q goes to 0 of xq. And that is, how do we want to write this, is, say the number of xi not equal to 0. So that is exactly the number of elements of x non-zero. So if I think about a vector, in that case, right, the only place it's gonna be 1 if I'm at 0, 1. If I go out this way, I'm gonna get what's gonna happen here? So this pink set here is the set of things where the 0 norm, which is the number of non-zero elements, is 1. Well, it's going to be the kind of 4 coordinates here. And so it's this really degenerate case. For example, if I looked at, what do I want to look at? If I look at the norm of 0, 1, the 0 norm of that's going to be 1. There's 1 non-zero element. If I look at the 0 norm of 1/2, 1/2, 2 non-zero elements, that will give me 2, etc. If I look at the norm of 0, 0, that will give me 0. So this is kind of, some cute little geometry you can play here. But these all, in some ways, behave similarly. I have to say, when q is less than 1, we don't technically get a norm. It won't satisfy the triangle inequality. But it behaves, in our case, it's useful to think about these things as kind of somehow related to norms. Okay, so why did we start talking about this? When we went up to to ridge regression, right? We had penalized this thing with the 2 norms. So I could actually add 2's here in all these places, right? So I could see it as penalizing beta, or penalizing my loss using the squared 2 norm, or constraining my betas using the squared 2 norm. And the question is, what happens if I use something else other than that 2 norm? So does it matter? Am I going to get the same answer? Does the geometry here somehow affect the solution we're going to get? Or affect how easy we can get that solution? And this brings us up to what's called the lasso. So let's write this out. So the official name, the shorthand name, is lasso, and that's how everyone will talk about this. It has a longer name, least absolute shrinkage and selection operator. So everyone just refers to it as the lasso. And the lasso is very much like ridge regression, but it's going to help answer this second question, which is, the first question was, can we do this variable selection? Can we solve the highly correlated problem in a continuous way? We could with ridge regression, where this continuous parameter lambda that kind of adjusted how we dealt with these highly correlated variables. And the second case is, can we actually get rid of variables in some kind of more continuous way, and actually get rid of variables, not just, because the beta hat for ridge regression is still going to have many non-zero many non-zero entries, if we got, somehow variable selection is like zeroing out entries of beta. And the question is, can we do that in a kind of continuous way? And that is called the lasso. And so it's going to have a very similar feeling where we're going to penalize, or we're going to constrain beta, but not using the 2 norm. Now, what would we like to do? So variable selection, maybe I should just say this explicitly. Variable selection is like zeroing out entries of beta, right? Because if I have, or maybe even beta hat, right? Doesn't really matter. Let's just say beta, right? Because my model is that y is approximately x beta, or is x1 beta 1 plus x2 beta 2 plus ... right? And so if I were to set this equal to 0, say force this equal to 0, that would basically be dropping x2 from my model. Right? Which is variable selection. That's what variable selection is. And so what we'd like to do is we'd like to force some of these betas to be 0 when we estimate. So when I estimate beta hat, my y hat is exactly equal to x beta hat. And if I were to force some of these to 0, they wouldn't actually show up in my formula anymore when I do my predictions, and I would somehow have selected them out and removed variables, which would not only help solve some of the issues related to kind of collinearity of my variables, but would help interpretability of my model, because I would exactly zero out certain variables. Whereas ridge regression will stop the beta hats from behaving poorly, but won't remove. I will still have a non-zero beta hat, potentially, for most of my variables, and they won't actually remove them in a way where if I actually zero them out, I would effectively remove them from my model. So before I say what Lasso does, when we looked at beta hat ridge, one way we had interpreted it is I was minimizing my squared loss subject to a constraint that the norm of beta is less than or equal to some threshold, right? And what we want to do is we want to maybe put a 0 norm on that. What would this mean? This would be that the number of non-zero elements of beta is less than or equal to t. So if t were 5, I would say I'm going to try to minimize my loss subject to the fact that the number of non-zero elements in this thing is less than or equal to 5, for example. Unfortunately, this 0 norm is not convex, and this is a intractable problem. Notice that, so non-convex, I mean, when I get to q less than 1, we go from this nice convex rhombus to this weird orange-shaped kind of non-convex shape, and then the limit when you go to the 0 norm, it just totally degrades. So for actually solving the optimization problem, which is to minimize that thing, that loss, that's not a good property. That's going to make it really, really hard to work with. We like convex optimization problems. Those are the easy optimization problems to deal with. So it's not convex. It's also just basically equivalent to the test all subsets of variables model, right? I mean, it's in some ways just equivalent to that. I just want to test all my variables and all subsets of my variables and choose the best one with less than or equal to t variables included. That's the same problem I've just stated here. And the problem is that it's computationally intractable for a large number of variables. So we can't do this. Directly. What we want to do is relax the problem, and we want to kind of approximate bounding the number of non-zero elements with what's called a convex relaxation. So we really want to solve this problem where we just count the number of non-zero betas and we limit that. Not tractable to do computationally. And so we're going to do solve the closest problem we can to that, but the closest convex problem. And the closest convex problem is where my bound is defined by this rhombus, which is when Q is 1. That is a convex constraint because it defines a convex shape there, a rhombus. If Q is less than 1, we're going to get a non-convex set. And so example Q is 1/2. That's going to not be tractable computationally in any kind of nice way. And so this green rhombus is called the convex relaxation of the harder non-convex problem. And so we're going to use Q is equal to 1. It's the closest we can get to 0, the 0 norm, which is what we actually want. But it still maintains the nice computable properties we have, namely that the constraint is convex. And so this leads to what's called the lasso, which, as I claimed, is similar to this. Beta hat lasso is where we're going to minimize that loss subject to the constraint that my 1 norm of my betas is less than or equal to some t. So it's as close as we can get. We can't use Q less than 1 because it's not convex. It's not going to be easily solvable. So we're going to have to use this 1 norm. The other way, so that's kind of way 1 of interpreting lasso. You can alternatively, just like bridge regression, think of it as a penalization where it adds some lambda times that 1 norm. That's an alternative viewpoint. Either you're constraining the 1 norm or you're adding a penalty to push it away from when that 1 norm is large. Now, we don't know if this is a good idea yet. In some ways, we're approximating what I'd really like to do, which is just count the number of non-zero betas and constrain that. So but the question is this really the closest convex relaxation of that problem, which is using the 1 norm, because 1 is closest to 0 while being convex. The question is that going to work for us? The annoying part about this is that, my third interpretation for ridge was that I could say that I could actually write out the solution. It was x transpose x plus lambda I inverse x transpose y. The annoying fact here about lasso is that while this 1 norm is continuous and convex, it is not differentiable. So no analytic solution. Think of it this way. The ridge was looking at the 2 norm. So it's basically looking at something squared, versus lasso is looking at the absolute value. So x squared, this is this nice differentiable function, and we can get a formula for the minimum of this thing very nicely by using calculus. If we look at, I I should put my y-axis in the right place there. If I look at the absolute value function, it looks like that. This is convex. It's continuous but not differentiable. And this one norm is basically the big boy version of absolute value function. So it's not differentiable. But it will otherwise be amenable. So the punchline is no simple formula for the Lasso estimator need to, let's say, numerically solve with convex optimization. So we give it to one of our lovely operation research buddies who does optimization, and they solve it for us. We're not going to worry about exactly how it's solved. There's been a ton of literature looking at how to solve this problem. So they're incredibly efficient ways of solving this at this point. But for our case, since this is not an optimization class, we're not going to look too much at how that's done. Okay. So is this a good idea? Is this actually going to get us anything different than ridge regression by penalizing with the one norm as opposed to the two norm? Doesn't feel like it, right? Shouldn't it just keep us away from large values of beta? You know, the ultimate goal is I want to do this way back up here. I want to do this variable selection. I actually want to zero out some of my betas, right? Because I said that if I can actually zero some of them out, which ridge is not going to do, I'm basically doing some kind of variable selection. So I actually want to force these things to be zero. Is that going to do it for us? The answer is yes, otherwise we wouldn't be talking about this method. So if you recall my picture for ridge, I had my OLS, ordinary least squares, beta hat, and I could draw my level curves for L of beta, something like this. And then I had my constraint, my norm of beta, my 2 norm squared, less than or equal to some threshold t, which said I want to live in this set. And this right here would be my beta hat ridge. And it would be the closest beta hat to the OLS beta hat, but lives in that disk, that blue disk. So this is ridge. And we can look at the same problem for Lasso. Okay. So let's see if I can draw this similarly. Here's my beta hat OLS. And I have my level curves that look something. Let's try to draw them. They're supposed to be kind of nested in a nice way. Okay, something like that. And now my penalty or my constraint is the 1 norm. So it gives me this in 2 dimensions, what's a rhombus, in higher dimensions called a rhomboid. This is my constraint that the 1 norm of beta is less than or equal to some threshold. Notice it's the 2 norm squared for ridge and just the 1 norm for Lasso. And notice at this point my level curves of L of beta don't intersect with my constraint. And we know from Calc 3 that it's the point of this intersection that defines, that will give me the solution, the constrained optimization solution. And you notice in my ridge regression, I end up in a place where I'm not on either of the coordinate axes. However, for Lasso, it turns out that it will often happen. I'm gonna cook the books here, but you're gonna have to believe me that this often happens. So let's draw. These are gonna be my level curves. Is that the point where my level curves intersect with my constraint is going to end up on one of my coordinate axes. So this is beta hat Lasso. And there's a couple ways to interpret that. One is just geometrically. my one norm constraint is kind of spiky, has really sharp edges to it. And whereas this two norm constraint for ridge has very soft, smooth edges. And the spikiness of this thing, and in higher dimensions, this really spiky kind of rhomboid thing, is going to mean that I'm more likely to hit this thing to intersect. My level curves are going to intersect on the coordinate axes. So here, I've hit it at this point. Why do we care about the coordinate axes, right? If you look at my ridge solution, this black point here, it is on neither coordinate axis, which means neither coordinate, right, beta 1, beta hat 1, or beta hat 2, is 0. I have not set either of those beta hats to 0. I haven't actually selected out variables. I've just constrained the beta hat in some nice way. For Lasso, if I end up on one of my coordinate axes, in this case, basically, notice that beta, let's say this is the beta 1 axis and this is the beta 2 axis. Beta 1 hat Lasso, the first beta hat for my Lasso estimate, is 0. So I've actually forced one of them to be exactly 0. And so I've basically selected out x1, or whatever is associated with beta 1 in my regression. So I've basically forced one of my betas to be 0, and I've therefore done a variable selection in some way. And so that's basically due to the geometry of this constraint, of this rhombus constraint. And so the geometry of the norm actually really matters. It actually is going to give me a different property of the estimator, where it's not just going to constrain my betas, but it's going to actually force some of them to be 0 and actually do some selection. And so Lasso is basically a continuous version of a variable selection. So let's just compare the methods. And for ease of comparison, assume that, what do I want to say? X is orthogonal. That is to say, the variables, you can basically interpret that as the variables are uncorrelated. I could do just a subset selection. We talked about this in last lecture with hard thresholding. And where basically I would say beta hat of my selected, let's call it maybe HS for hard thresholding, is beta hat, the ith beta hat, the ith component of beta hat is going to just be that ith component of beta hat if the absolute value of this thing is large enough, is bigger than my threshold, right? So it's basically, I'm going to leave it unchanged if large enough or 0 elsewise. I'm going to select it out. So that's kind of a hard thresholding procedure. We have ridge, and in the case where our variables are uncorrelated, the ridge solution really, really, really simplifies. You can actually show, this may be a good homework problem, that the ridge solution is just my OLS. So this is OLS, let's say. Let's just write OLS, right? Is my ordinary least squares estimator divided by 1 plus lambda. So what this is called is proportional shrinkage. I'm just shrinking all of my beta hats by 1 over lambda. As we said, it's a shrinkage operator. The third is Lasso. And Lasso, beta hat Lasso, is has the following form. We're going to look at the sign of beta hat OLS, so the ith component of my lasso beta hat. We're going to preserve the sign, so the sign function just preserve the sign, and then we're going to look at this maximum of the absolute value of beta, of the OLS beta hat, minus lambda and 0. So that's a weird thing. But basically what it does is it's going to look at the absolute value of my beta hat and subtract off lambda. If that is less than 0, I'm going to 0 it out. If it's bigger than 0, so maybe I can just write this out, it's going to just leave it alone. So this thing is basically going to be how do we want to write this? It's going to take the OLS beta hat, it'll subtract off lambda if this is bigger than or equal to 0. Otherwise, if I do that kind of thing, it will, if it subtract this off and it's less than 0, I'm going to 0 it out. Of course, the reason you have to be careful, it's going to either be plus or minus that. It's going to maintain the sign. So it's always going to shrink it towards 0. But let's just leave it like this. This is kind of inspiration. This is true. For positive beta hats. And for negative, it's going to be, let me draw the picture. The picture will make this much more obvious. So here's our picture. Here's our hard thresholding. Which is that here's my 45-degree line. Here's my axes. So on my x-axis, I'm going to have beta hat I, and on my y-axis, I'll have the hard thresholded version. And there's some threshold here, t. And what's going to happen is if my beta hat is either above t or below t, it's going to leave it alone. And if my beta hat either is positive and goes below the threshold or negative and goes above that threshold, it's just going to 0 it out. So it's basically going to 0 this whole thing out like this. You can think of like a connected line here. So it's basically, it's going to leave everything alone that's large enough in absolute value. But if it's too small, it's below this threshold, it's going to 0 it out. Hard threshold. You're in absolute value below the threshold, you get 0'd out. The proportional shrinkage is, let's draw the axes here. Here's my 45-degree line. Proportional shrinkage is just going to kind of shrink everything. So it's going to fit it on a line like this. It's going to shrink everything towards 0. So it's basically moving all of my beta hats. So this is beta hat OLS, and this is beta hat I ridge. So it's basically just squishing them all towards 0. It pushes them either the positive one's close to the 0 and the negative one's close to the 0. Right? And the slope of this thing is 1 plus lambda. So it doesn't 0 anything out, right? The hard thresholding, if they get close enough, if you have a beta hat I, if it's over here, you're okay. But if it gets over here, if it's too close to 0, just kills it, 0s it out. So it does 0 out things. So it actually does select things, right? This is basically our variable selection. Proportional shrinkage doesn't ever 0 it out. It only would be 0 if it already started at 0. It's always just going to kind of shrink it down and control it. This is ridge regression. And the last one is so-called soft thresholding, or lasso. I should write this. So this is called a soft threshold. And soft thresholding Here's my 45-degree line. Here's my beta hat OLS. And here's my beta hat lasso. Oops, let's write this out, lasso. What's it going to do? It's going to shift everything by 1 over lambda. So it's going to shift up by here. It's going to add, sorry, not 1 over lambda, or it's going to shift positive ones down by negative lambda. And then if I shift these and that crosses 0, I'm just going to 0 them out. So this is positive lambda, this is negative lambda. So it's basically saying it's a kind of more continuous version. It's somewhere between this ridge and the hard thresholding, which has this discontinuous jump here. This is continuous. It's not differentiable. It has a hard angle here, right at this point, right? But it is a differentiable version. So it's basically shrinks it down, and then if it's too low, it zeroes it out. So that's another way of thinking about ridge, but about lasso. So lasso is, unlike ridge, which is just going to control the betas, is actually going to zero out some betas. Now, in the last couple minutes here, I just want to note two things. One, we can combine ridge and lasso. So one of the other questions you might have is there a value other than 2 or 1? Should we work with the 1.5 norm or the 3 norm? You could. It's probably not worth it. What people do is they combine ridge and lasso, and this is called the elastic net. And beta hat elastic net is can be written as, you basically have a combination of a 1 norm penalty and a 2 norm penalty. So you minimize your loss function plus lambda, and then I'm going to combine 2 penalties. I'm going to have both a 1 norm penalty and a 2 norm squared penalty. And I'm going to balance a trade-off between these using some other parameter called alpha. So I'm just going to take a weighted combination of these. So alpha is some number between 0 and 1, which tunes the trade-off between the 1 norm and the 2 norm penalty. So alpha is 0, gives us ridge, and alpha is 1, gives us lasso, right? If alpha is 1, the 2 norm penalty goes away, you just get a 1 norm penalty. And if alpha is 0, you don't get the 1 norm, you just get 2, so you get ridge. And lambda here still is kind of an overall penalty for the things. So this is what people do. It's called the elastic net. It will both deal with, it will select out some things, and it will help you deal with collinearity of variables. The second thing I want to mention is that you can do this with other, maybe I should say specifically what I mean this, can do penalization with any method, basically. We've done it in terms of regression, and that's where it's first developed. Ridge regression ridge was developed in the 70s, and lasso was kind of first developed in the late 90s, I think. But since then, there's been a ton of research on other things. So, for example, we could penalize any you can penalize any loss. So we talked about how you're ultimately in these, you're minimizing some loss. You can penalize any loss. For example, you could do a penalized logistic regression, which people do a lot. Either 1 penalized or a 2 penalized, and it would help you, or a combination of a 1 norm and 2 norm penalization. It'll help you deal with collinearity among your covariates in a logistic regression, or if you want to select out variables in your logistic regression, you can do these kind of things. The problems are more complicated, They're not as easily solvable as the regression problem where they're originally developed, and there's been a lot of research there. But you can add on penalties, and in a similar way, adding on a 2 penalty will help deal with non-regular problems where you have regularity problems, where you have collinearity among your covariates, and adding on a 1 penalty will help hopefully push some of your estimates to 0 and do some kind of variable selection. So there's a whole wide world out there, and you'll see a whole lot of stuff of people doing this in many kind of methods. So just as an FYI, and we may look at logistic regression if we get some time, L1 or whatever, any kind of penalized logistic regression. But that's a real quick overview of Lasso and how it connects to variable selection. It's basically a continuous kind of variable selection. And we'll stop there.